Okay.
Welcome everyone. This is the second lecture of the mini course that we are running on algebraic number theory. This lecture is run by both Srijan Das and Akashdwip. Today Srijan Das will be presenting the second lecture. Without further ado, let's jump in. Srijan, are you ready?
Yeah.
Yeah. So I'll mute myself. So anyone who has a question, feel free to interrupt. Unmute yourself, and the speaker can try to answer. Yeah. Thank you.
Okay. So this is the second lecture on this mini course. Last day, Akashdwip spoke about integral extensions, number fields, and number ring of integers, discriminant those things. I will proceed from there, and today first half will mainly, not first half, the whole lecture will mainly be focused on mainly commutative algebra. Those techniques are really useful and will actually prove a important result in algebraic number theory, that is unique factorization of ideals in Dedekind domains. So let's start. So we'll start with discrete valuation. So at first I give the definition of evaluation. Evaluation on a field K is a group homomorphism from the multiplicative group of K to R such that the relation V valuation of x plus y greater than equal to minimum of valuation x and valuation y. This condition satisfied. So this is the definition of valuation, and we can extend the notion of valuation to the whole field by defining the valuation of origin as infinity. So the image of V in the R is called the value group of V, and we say V is a discrete valuation if the value group is equal to Z. Now, in fact, every discrete subgroup of R is isomorphic to Z, so it is not necessary that we should get Z as the image of V. We can get any discrete subgroup of R as the image of V, and we can rescale. So if the image of V is a discrete subgroup of R, then we can say this is a discrete valuation. Now, a valuation ring. What is a valuation ring of a field? A valuation ring of a field is the collection of elements which have the positive valuation. That's Vx is greater than equal to 0. And a discrete valuation ring is an integral domain that is the valuation ring of its fraction field with respect to a discrete valuation. It is pretty much clear, and we can verify that every valuation ring that set elements which have positive valuation has forms a ring. So the name ring is quite right, and the fraction field of this ring A is K. Now, for any x in the multiplicative group of K, that is K minus origin, we take the valuation of x inverse. We can see that the valuation of x inverse is a negative of valuation of x. So we can say that at least one of x or x inverse has a non-negative valuation, and we see that the ring valuation ring is the collection of elements with the positive valuation. So we can say that any one of x or x inverse lies in A. So if x has positive valuation, then x inverse has negative valuation. So x in that case x lies in A, but x inverse not, and same for vice versa. So we can see that x is invertible if and only if valuation of x is 0. So the unit group of A is nothing but those elements, a collection of those elements which have valuation 0. Now we can from what we have seen that we can partition the non-zero elements of K according to the sign of their valuation. So elements with valuation 0 are units, elements with positive valuation are non-units, and elements with negative valuation actually doesn't lie in A, but their inverse are actually the non-units in A. So this classification motivates us to the following more general definition of a valuation ring. The general definition of valuation ring is a valuation ring is an integral domain A with fraction field K, with the property that for every x in the field, either x is in the ring A in the integral domain A, or X inverse is in the integral domain A. So let us now suppose that integral domain A is the valuation ring of its fraction field with respect to some discrete valuation V. As the valuation of the image of the valuation of the ring is the all positive integers and 0, so there is an element pi in A, we can say, whose valuation is 1. So we tell that pi as the uniformizer of the valuation ring A. Now if we fix an uniformizer A, each element of x of k star can be written as x is equal to u pi to the power n. How can we say that? Let's say if we have a valuation defined on k, so take the valuation of x. If it gives n, so then take the element x by pi to the power n. So v of valuation of x by pi to the power n is valuation of x minus valuation of pi to the power n. So valuation of x is n, valuation of pi to the power n is n. So valuation of x by pi to the power n is 0. And we know that the valuation 0 elements are actually the units. So x by pi to the power n is actually u. So from that, where u is a unit. So from that we can write that x is equal to u pi to the power n. So this actually gives an important result. The result is every non-zero ideal of the valuation ring A is equal to is actually a principal ideal, which is generated by any pi to the power n. So moreover, we can say, so we can see that every ideal is actually PID. So it is an UFD. So valuation ring is an UFD. So moreover, the ideal depends only on n, because if we take another uniformizer pi dash will be always be equal to u into pi for some unit u. So the ideals of A are thus totally ordered, because pi all ideals are pi to the power n, pi to the power n plus 1, pi to the power n plus 2. So in this fashion, all the ideals are totally ordered, and the ideal that generated by pi, which is actually the collection of all the elements in the ring, which is strictly positive valuation, gives the unique maximal ideal of the ring A. So we have seen that a valuation ring is a PID which have a unique maximal ideal. Now we came to definition. The first definition is a local ring is a commutative ring with a unique maximal ideal. So we can say that a valuation ring is a local ring. Now the second definition is the residue field of a local ring is the maximum with the maximal ideal M is the field A mod M. Now what is an example of valuation ring? We can take the ring Z and localize it to a prime ideal P. So that ZP is a valuation ring of the fraction field of ring of fraction field of Q, and the maximal unique maximal ideal is the ideal generated by P. PZP is the unique maximal ideal, and the residue field is ZP mod PZP, which is actually isomorphic to Z mod PZ, the finite field of order P. Now, discrete valuation rings are in many respects the nicest rings which are not fields. In addition to being an integral domain, every discrete valuation ring enjoys some of the following properties. First property is Noetherian. Why it's Noetherian? Because we have clearly proved that it is a PID. So PID means Noetherian. So again, we have proved that it's a local ring. And very important property of discrete valuation ring, it is a dimension one ring. Dimension means the maximal length of a chain of prime ideals. So dimension 1 actually means that every non-zero prime ideal in the discrete valuation ring is actually a maximal ideal. So another property of the discrete valuation ring is regular. What is regular? In a ring we call regular if the dimension of that ring, which we've defined earlier, dimension of that ring is equal to the dimension of the vector space M maximal ideal M mod M square as a vector space over the field A mod M. So this is the definition of a regular ring. So discrete valuation ring are also regular. Discrete valuation ring are also integrally closed in their fraction field. So we call that discrete valuation ring are normal. That is normal. And the final property is discrete valuation rings are maximal, in which says that there exists no intermediate rings strictly between the discrete valuation ring and its fraction field. So these are some very nice, beautiful properties of the discrete valuation rings. Now we can say we have seen that very nice properties of some discrete valuation ring, but certainly all of those are not a necessary condition. So we now see how we can characterize discrete valuation ring. That is, which combination of properties are enough to give you a discrete valuation ring. So now the next theorem. The next theorem says for an integral domain A, the following are equivalent. A is a discrete valuation ring. A is a Noetherian valuation ring that is not a field. A is a local ring. A is a PID, which is not a field. A is a normal that is integrally closed Noetherian local ring of dimension 1. A is a regular Noetherian local ring of dimension 1. A is a Noetherian local ring whose maximal ideal is non-zero and principal. Finally, A is maximal Noetherian ring of dimension 1. Any of these property is a definition of the discrete valuation ring. Now, next
Srijan?
we yeah. Yes.
So what is the meaning here? What is the context for maximal here?
Maximal means that there is no intermediate ring strictly between the ring A and its fraction field.
I mean, that's another DVR, right? Like the intermediate
No
ring is a DVR.
Yeah, definitely.
Okay.
Yeah. So now we go into discussion of Dedekind domains. So before discussing Dedekind domains, we are looking some historical context of it. So how the Dedekind domains rise in the algebra, in the realm of algebra. So when it first emerges from the work of Kamar. Kamar tried to prove the Fermat's last theorem, the infamous Fermat's last theorem, and he made a huge error. That he assumed that in all the number rings, he assumed the unique factorization holds, but which is absolutely not true. Unique factorization is the unique factorization of elements of that number ring, which is an absolutely not true statement. So in order to fix this, Dedekind comes up with an abstract algebraic structure where unique factorization of elements may not hold, but at least the unique factorization of ideal absolutely holds there. So this is the main target theorem of today's lecture will prove, and this is the context how the Dedekind domains arise in the realm of number theory. Now we define the equivalent condition of defining Dedekind domains by this proposition. The proposition says the let A be a Noetherian domain. The following criteria are equivalent: that if for every non-zero prime ideal P in A, the local ring A P is a DVR. And the second condition is the ring A is integrally closed and dimension of A is less than equal to 1. Now the next definition is that says that whichever Noetherian domain satisfies one of these equivalent condition is called a Dedekind domain. Now for every PIDs are Noetherian, PIDs are UFD, so we know UFDs are integrally closed, so PIDs are integrally closed, and trivially PIDs are of dimension 1, so every PID is a Dedekind domain. In particular, Z, the ring of integer, is a Dedekind domain, and Kx, the polynomial ring, both of these are PID, so these are Dedekind domains. Now, where do we use this construction of Dedekind domains in number theory? Main point is the ring of integers, which is so important in studying algebraic number theory, is a Dedekind domain. Yes?
Maybe it's better if you tell people what are the prime ideals in the localization so that they can easily see why those things are true.
Oh, okay. What are the prime ideals? The prime ideals in local AP, you know that what is the localization of AP? It is actually the localization with respect to the multiplicatively closed set A minus P. So if we localize with respect to that multiplicative set A minus P, then we get A subscript P. Now, what are the prime ideals in AP? Actually, what are the prime ideals in general in a localized ring S inverse A? The prime ideals in localized ring S inverse A are in actually we could calculate with it by a one-to-one bijection with the prime ideals of A. How we get these prime ideals? We take a prime ideal P in A, which actually does not intersect S, and we take those P to S inverse P. So those S inverse P where P does not intersect S are the prime ideals in the localized ring S inverse A. So here AP in the localized ring AP, from definition we can easily see that the prime ideals in AP are the correspond to the prime ideals of A, which is absolutely contained in P. So these are the prime ideals of the localized ring AB. Now we get back to ring of integers. So ring of integers, why they are determined domains? We go by the second definition equivalent condition. From the definition, it is clear that ring of integers are integrally closed because we take the integral closure of the ring of integers in a number field. And why it is Noetherian? Because from a result in module theory, we can say that Z is a free module of a finite rank. Actually, the rank is equal to the degree of the number field. So as Z ring of integer is a free module over Z, so it is a Noetherian. And why dimension A is equal to 1? It is a quite tricky proof, but I'm saying it. If we take a prime ideal in the ring of integers, we have to show that prime ideal is a maximal ideal. So what we do, we take we take the okay, yeah. So we take a prime ideal in a ring of integers. So we contract that prime ideal to the ring Z. So we know that contraction of a prime ideal is a prime ideal. So we return to the prime ideals of Z, which are P, but P these are also maximal ideal. So in a result of integral extension says that if we take a prime ideal in integral extension, we contract it, then we arrive at a maximal ideal, then the prime ideal which we starts with is actually a maximal ideal. So by this result, we get that the first prime ideal in ring of integer is actually a maximal ideal. So the ring of integer we can say integrally closed, dimension 1, and it's Noetherian. So the ring of integer is actually a Dedekind domain. So now let's assume that A is a Noetherian domain. We do not necessarily assume that it's a Dedekind domain, and K is its fraction field. Next definition is it's an important concept in number theory that a fractional ideal. What is a fractional ideal? The fractional ideal of a Noetherian domain A is a finitely generated A submodule of its fraction field. Fractional ideal actually generalizes the notion of an ideal. When A is Noetherian, the ideals of A are precisely the finitely generated A submodules of A. And when is also domain, we can extend this notion to fraction field. But the important note is here, note that not every ideal is a fractional ideal because ideals are contained in the ring, but fractional ideals not necessarily contained in the ring. Fractional ideals are actually contained in the fraction field of the ring. So now this is a quite abstract definition of fractional ideal. To compute things, we have to reach at a more easy definition where we can actually see how the fractional ideals look like in a Noetherian domain. So next lemma tells us that let A be a Noetherian domain with fraction field K and let I inside K be an A module. Then I is finitely generated if and only if there exists an element in A such that AI is contained in A. This dilemma tells us that the every fractional ideal looks like 1 by A into I form, the last corollary which says that, where 1 A is an element of A and I is actually an ideal in A. So this is the first structure of an fractional ideal. So this lemma also gives an alternative definition of fractional ideal. which can be extended to domains that are not necessarily Noetherian. There is submodules I of K for which there exists a non-zero R in A such that Ri in A. When A is Noetherian, these two definitions is clearly coincides. Now, a fractional ideal of A is principal if it is generated by one element, that it is form XA for some X in field K. It's not that it is in K, not necessarily it is in A. So we'll also use the notation X1 brackets to denote the fractional ideal. So as with ideals, we can also addition and multiplication we can do for fractional ideals. It is trivial. For any two fractional ideals I and j, I plus j is the ideal generated by I plus j, where I is in I, j is in j, and the multiplication of fractional ideals ij is the ideal generated by ij. So here the notation generated by S means a module generated by S in the fraction field K. Always we do in the generating kind of things we all do in the fraction field K. Now these are all similar to ideals. Now the next thing is quite new. Not quite new, we do in a fractional ideal also, that colon ideal, but in case of fractional ideal, this generally is the notion of division in a field. We also have a new operation corresponding to division, that is for any fractional ideals I and j, we define the colon ideal, that is x belongs to k, such that xj, that fractional ideal, is contained in I. This is called a colon ideal. If I is generated by x, that is I is a principal fractional ideal and j is principal fractional ideal, then the colon ideal I is to j is generated by x by y. Now the main, a very important lemma, the lemma says us that if I and j are fractional ideals of a Noetherian domain A with j non-zero, then I is to j, I colon j is a fractional ideal of A. This lemma will help us in next. So now a definition, a fractional ideal I is invertible if ij, the multiplication of two fractional ideal ij, is A for some fractional ideal j. That is, there exists some fractional ideal j such that multiplication of I with that ideal is A. Now inverse, we can easily show that inverse are unique when they exist. And we use the notation I inverse to denote the inverse of the fractional ideal I. Now, the fractional ideal I of A is invertible if and only if I into A is to A colon I is A. So the colon ideal actually represent the notion of inverse. We always note that the I into A colon I is always in A. It is trivial to check, for it holds always. But the lemma states that this inclusion is an equality precisely when I is invertible, that there is then j such that ij is equal to A. That is, we get I is invertible if I into A is A colon I is A, and if that I A colon I is equal to A, then I is invertible. So A is now assume A is a Noetherian domain, not necessarily a Dedekind domain, and K is its fractional field. Now ideal multiplication is easily can check its commutative, it's associative. The set of non-zero fractional ideals of a Noetherian domain so form an abelian monoid under the multiplication with the identity ideal. So it follows that the subset of invertible fractional ideal is an abelian group. The ideal group IA of Noetherian domain A is the group of invertible fractional ideals. Note that despite this name, in the elements of IA need not be ideals. We call this ideal group, but this is actually the group of invertible fractional ideals. For the
Srijan,
print, yeah.
So isn't always I times A colon I A?
No.
So
That's what we say now, that
what
IJ should be, that I into A colon I is always contained in A, but if the equality should hold, then we have to, we need that I to be invertible, that there exists an J such that Ij is equal to A.
Oh, okay. If you know the ideal is invertible, then this thing holds. Okay.
Then these things happen, and if this thing happens, then it is invertible.
Okay.
So every non-zero, we say that every non-zero principal fractional ideal X is invertible. Why? Because the inverse is actually the fractional ideal generated by X inverse, the element X inverse. And the product of principal fractional ideal is principal because multi xy is equal to the ideal generated by xy, and unit ideal is also principal. So you can say that the set of non-zero principal fractional ideal is a subgroup of the invertible fractional ideals. Now let it be a Noetherian domain. The quotient of the set of non-zero fractional ideals by the non-zero invertible fractional ideal by the principal fractional ideal is called the class group of A. It is also called the Picard group of A. Now, example, we discussed about DVR. Now, if A is a discrete valuation ring with uniformizer pi, then its non-zero fractional ideals, which are the principal fractional ideals, which are generated by pi to the power n, with n is in the integer. Here is an important point, that the ideals of the DVR are form pi to the power n, where n is either strictly positive or it is zero. But when we is dealing with principal fractional ideals, in that case n comes from the whole ring of integers, whole is z. I don't use the term ring of integer here. So the ideals, fractional ideals, are of form pi to the power n, generated by pi to the power n, where n is in z. We have the multiplication of the principal fractional ideals, pi to the power m into pi to the power n is generated by pi to the power m plus n. Thus, we see that the ideal group of A is isomorphic to Z, and in this case, all the invertible fractional ideals are actually principal fractional ideals. So the class group here is trivial. So for all discrete valuation ring, class group is trivial. Now, one of the most important theorem in this lecture is here, that let I be a fractional ideals of a Noetherian domain A, then I is invertible if and only if its localization at every maximal ideal of A is invertible. Equivalently, if and only if its localization at every prime ideal of A is invertible. We give the proof of this theorem. Suppose, let's assume I is invertible. We show that, actually we see that 2 or 3 slides ago, that I is invertible means ij is equal to A, which is equivalent to the condition I into A colon I is equal to A. And we localize the product, the localization commutes with the multiplication of fractional ideals. So I localized at M into A localized at M colon I localized at M is A localized at M. So by the equivalent condition, again we can say I localized M is invertible in the Noetherian domain A localized at M. Now the reverse condition, that if I localized at M is invertible for every maximal ideal M, then we can say again by that equivalent condition that I localized at M into A localized at M colon I localized at M is A localized M. Now we want to show that I into L colon I is equal to A. How we show that? It is a famous result of commutative algebra, that in the Noetherian domain, that I is equal to the intersection of I localized at M, the intersection runs over all the maximal ideals. And this intersection is same as the intersection of I localized at P, where P is the prime ideals and the intersection runs over whole the prime ideals. So L colon I is same as the intersection of those things. Similarly, we get those things, and using that I localized at M is invertible, we get that finally this equal to intersection of A localized at M, and again using that result from localization, we can say that this intersection is equal to A. So we arrive that A colon I is equal to A, which says that I is invertible. So the similar proof, of course, we can run with the prime ideal, because the ideal actually used in the intersection, and we know that the result of localization is true in case of prime ideals also. Now, why this result is important? Corollary says that in a Dedekind domain, every non-zero fractional ideal is invertible. Why? We know that Dedekind will if localized the Dedekind domain at a prime ideal, then we get DVR. That's one of the first condition of Dedekind domain we see. So in the as the DVR is PID, so we have seen that already it is all the maximal ideals are clearly invertible, because if it's generated by X, then its inverse will generate by X inverse. So clearly we see that if we localize the Dedekind domain, then every ideal is invertible. So in a Dedekind domain, every non-zero fractional ideal is invertible. So the more we arrived at the conclusion that at the Dedekind domain we form the set of fractional ideals is actually a group, which is not true for in any Noetherian domain. In Noetherian domain, we take the set of invertible fractional ideals, but in the case of Dedekind domain, we take any ideal, its inverse exists. So in the case of Dedekind domain, all fractional ideals are invertible, and it forms a group. Now in lemma, a lemma says this lemma will be important in the proof of the final theorem of this lecture. And the lemma says that let A be a Dedekind domain, and small a is an element of A. A set of prime ideals that contain A is finite. We will actually use the corollary of this lemma, which says that I be a non-zero ideal of a Dedekind domain A. The number of prime ideals of A that contains I is finite, because for we take any x from I, then we apply the previous lemma. It's trivially follows from the lemma, the corollary.
Srijan, just a second,
Yeah.
can you show that lemma and corollary?
Yeah.
Yeah, fine.
Yeah. Okay. So we continue. Now we have a very important definition. We actually now define a valuation on the set of invertible fractional ideals. Here we deal with the Dedekind domain. So we don't need we don't say the word invertible fractional ideal. We say the only fractional ideal, because all fractional ideals are invertible in Dedekind domain. Now let P be a non-zero prime ideal in a Dedekind domain A with the fraction field K, and pi be a uniformizer for the discrete valuation ring A localized at P. Let I be a non-zero fractional ideal of A. Now we want to define the valuation of that fractional ideal I. How we define? We localize the ideal fractional ideal I at P. We get IP, which is the non-zero fractional ideal of the Dedekind domain AP. Hence, it is of the form generated by pi to the power n, where n is in Z. So now we define the valuation Vp from the ring of fractional ideal to Z union infinity by defining the valuation of that ideal I as n, and if we get the zero ideal, we define the valuation of that zero ideal as infinity. So thus we define a valuation on the ring of fractional ideals of a Dedekind domain. Now we can easily check from the definition. Basically, we can check that this valuation is a group homomorphism. The map Vp is a group homomorphism, and it is order reversing with respect to the partial ordering on the set of fractional ideals, and the total order on the that is if we take any ij in the set of fractional ideals, if I is a subset of j, then valuation of I is greater than equal to valuation of j. So that's how we define the valuation on a fractional ideal, set of fractional ideal. Now important lemma that we say that let P be a non-zero prime ideal in a Dedekind domain A. If I is an ideal of A, then valuation of I is 0 if and only if P does not contain I. In particular, if Q is another non-zero prime ideal different from P, then as this is a Dedekind domain, we know this every prime ideal, non-zero prime ideal is maximal. So P does not contain Q, Q does not contain P. So valuation of P with respect to prime ideal Q and valuation of Q with respect to prime ideals of P all are 0. Now from corollary of the lemma says, let A be a Dedekind domain with fraction field K. For each non-zero fractional ideal I, we have valuation of I at P for all but valuation is 0 for all but finitely many prime ideals P. In particular, if X is in the K star, then valuation of X is equal to 0 for all but finitely many P. What is the proof? If we take an ideal in A, the last corollary that in the previous slide, we can say easily from the previous lemma, because we say that it contains in a finitely many of ideals, prime ideals. So it is valuation of, so the last corollary and this lemma, the lemma in this slide, both simultaneously imply that if I is in the dedicated domain A, then we can say that VPI is 0. Now the case is if I is not is not a subset of A, then it's a fractional ideal. From the definition of fractional ideal, we can write I as 1 by A into J, where J is an ideal of A and A is an element of A. Now we can, from the basic property of the valuation map, we can say VP of I is equal to VP of J minus VP of A for all but finitely many prime ideals A. And these holds in particularly for I is equal to X for any X belongs to K star. So VP of A is equal to, we say that VP of A is 0 and VP of J is 0. So we can say that VPI is equal to 0 minus 0. So this is 0. So there we have the corollary that VPI is equal to 0 for all but finitely many prime ideals P. Now we are now ready to prove our final theorem. The theorem of today's final theorem of today's lecture is, let A be a dedicated domain. The ideal group, that is the fractional ideal set of fractional ideals IA of A, is the free abelian group generated by its non-zero prime ideals P. That is, in the symbol, there is an isomorphism IA is direct sum of Z, where the direct sum runs over the prime ideals of P. This isomorphism is explicitly given by, we take a fractional ideal I, we then map it to all the VP, all the ordered pairs of VPI, where P is the prime ideals, and the inverse map is, we take any element from direct sum of Z, and we make them we send them to product of P to the power EP, where the product runs over the prime ideals. It is actually reminds us about the factorization in the natural numbers or the ring of rational numbers. Now, proof of this theorem. From the last corollary, it implies that the first map is well defined. What is the first map? That we send I to the ordered pairs of VPIs. Why? The vector space associated to I it has only finitely many non-zero entries, because we say from the last corollary we say that finitely many VPIs are non-zero, rest are 0. So in direct sum we know that finitely many elements in the ordered tuple is 0. So it is well defined by that last corollary. Now for each non-zero prime ideal P, the maps I goes to the valuation of I, and the inverse map P goes to e to the power P are the group homomorphism, and it follows that there is a mistaken slide. It will be E subscript of P, not P e to the power P. So the map I goes to VP of I and P goes to E subscript of P are group homomorphism, and it follows that the maps from the theorem are both group homomorphism, because these are some composition of these homomorphisms. Now to see that the first map that I goes to the ordered pairs, ordered tuples of VPIs is injective. How we can show that? We go by each element by element. So VPI is equal to VPJ implies, from the definition of the valuation, we can say that VPI is equal to VPJ is equivalent to the condition IP is equal to JP. The IP is equal to JP. So, and if this holds for every P, again we use that result from commutative algebra, that I is the intersection of all IP, where the intersection runs over P, and which is equal to the intersection of JP, as all IPs are equal to JP. So intersection of JP is equal to J. So we get the result that I is equal to J. So this map is injective. Now we see that this map is surjective. We can see that we see that from the equation in the slide, that VQ for any vector we see that EP in the image we have VQ of the product of P to the power EP. We expand this product by the property of valuation as summation of EP of VQP, and we know that the VQP is 0 if not is equal to 0, only if that P is equal to Q. So all terms actually go vanishes, only the terms with the P is equal to Q remains. So we get that EQ into VQ of Q. VQ of Q we know 1, so it is VQ. So this implies that this element, the map is surjective, which actually implies that P of e to the power P is the pre-image of the order table EP. So it also shows that the second map, that is second map will define EP goes to P to the power EP. This is inverse of the first map, I goes to VPI. Now the corollary from this definition is what? This is the most important result. This is not the corollary of the theorem. This is actually corollary of the explicit map we give, that every ideal I we take here in the theorem, we take it to the VPI, we take its inverse, so it goes to P to the power VPI. So every ideal I can be written as the product of P to the power EP under non-zero prime ideals P. So the final remark is this is a true, this converse of this result is true, that every integral domain with unique ideal factorization is a Dedekind domain. It is a quite tough result, but it is true. Thank you.
Srijan, what is the rank of the IA? Is it finite?
The rank of IA.
Yes.
It is equal to the cardinality of the prime ideals.
Yeah, but do we know in certain situations where okay, that's not. Yeah, this is just primary. So thank you. Yeah. Does anyone else have any question? Yeah, if no one has any question,
Okay.
let's thank the speaker and end it here.
Okay. Thank you.